So last time we have derived the product rule and quotient rule for differentiation, and done some problems based on them. Especially, we obtained the derivatives of more trigonometric functions, that is tan x, cot x, secant x, and cosecant x. So what we have so far cover most of the elementary functions. So the elementary functions are polynomials and generally other algebraic functions. You want me to explain the fifth problem? This one. Okay, I've written the answer here already. So let us look at how that goes in detail. So you are differentiating term by term. So when you differentiate this, you can use quotient rule. I'm using product rule and chain rule. So I'm considering this as 1 by x d dx of sine x square plus sine x square d dx of 1 by x, normal product rule. Is that clear? We'll take u as sine x square and v as 1 by x. Okay, you don't need to write this. I'm just telling you what I've done. So this is u dash v. Okay, this first term is u dash v, where this is u dash and this is v. Just writing the undifferentiating or non-differentiated term first. That's all. But it's u dash v and plus uv dash, right? Okay. So now what is this? Sine of x square, when you differentiate, you have to apply chain rule there. So 1 by x remains there. That is this v rather. This v remains there. And sine of x square, when you differentiate, you get by chain rule 2x cos x square. Correct. 2x being the derivative of x square, and then derivative of sine is cos. So 2x square, 2x is the term obtained by differentiating the inner function x square, and then after that you multiply the derivative of sine of x square with respect to x square, which means you just change sine to cos, and that gives you this. That's the first term. And then sine of x square, the second term, sine of x square, this term is here as it is, and then you have to differentiate 1 by x. Remember that derivative of 1 by x is minus 1 by x square. It's, as I told you, it's better to remember that, but you can also do it as x raised to minus 1 is being differentiated. So x to the n differentiation is n x to the n minus 1. So x to the minus 1 differentiation is minus 1 x to the minus 2. So that is minus 1 by x square. So this. Okay, now if you just simplify this, in the first you get 2 cos x square because the x gets cancelled, and the second one is just minus sine of x square divided by x square. Remember, this is sine of x square, it's not sine square x. Whenever we write it this way, there is always, even without writing, this bracket is there. It's sine of x square, not sine square x. All right. Okay, so we get this. That is the first term differentiation. And now if you differentiate the second term in the problem, that is this, you have d dx of cos of x square. So how do you do that? Very similar to what we did just now with sine of x square. Here we have x square, so its differentiation is 2x, and then cos differentiated gives minus sine, so minus sine x square. So this is minus 2x sine x square. Okay, So the final answer is this plus this, which I have written here. 2 cos x square minus sin x square by x. Oh, okay. I missed the 2 when I copied it here. There is a 2 here already. So we'll get 2 here. And therefore, minus 4. Okay. So, yeah, in the final answer, you have minus 4x sin x square. You just missed this 2. Okay. So now, the elementary functions are algebraic functions like polynomials and functions involving radicals. Radicals are square roots. And so those, and then anything, sorry, anything else that you can obtain by if you add or multiply polynomials, you just get more polynomials, higher degree polynomials or other polynomials. So if you divide two polynomials, that's still called an algebraic function. Okay, that's one kind of elementary function. So algebraic functions. Then you have the exponential function. So e to the power of something. And then you have sine, cos, tan, and those are trigonometric functions. So these are some of the elementary functions. There are a few more. The others are basically the inverses of these functions. So the inverses of these are, if you, I don't mean reciprocal, I mean inverse. So polynomial functions don't really have inverses other than if you mentioned square roots, for example, that's there. So that's already covered. What else is the inverse? What is the inverse of exponentiation? If you take e power x, what is its inverse? So again, I don't mean e to the power minus x. So if you write y is equal to e power x, then what is x in terms of y? How do you write x in terms of y? So if I say y is equal to, or let me write e power x is equal to 1. And now I'm asking, what is the value of x? What does this mean? What is that value of x for which e power x is equal to 1? This is the meaning. So in general, if you ask what is that value of x for which e to the power x is a given value y. So y is not being calculated here. Suppose I give you the value of y and then ask what is the value of x that gives this particular value of y when you take e to the power x. Then that is this function. That gives you a function. So that is this function. So in other words, if you apply that function to 1, then you get some answer here. What is that answer? E to the power of what is 1? To get 1, you should take e to the power of something. What is that? Any idea? Okay, you're telling me the inverse function. So in this particular, this one, no, e to the power infinity is not 1. E power 0 is 1. Yes. So e to the power of 0 is 1. Yes. Okay. So in general, yes, this is the log function. In general, you're right. This is log, right? So the inverse function of exponential function is log, where of course, whenever I write log, I always mean log to the base e, not log to the base 10, which is also written as ln, okay? Natural log, which stands for natural log. It's natural log because it is the inverse of this e, and that is the default log in mathematics, okay? physics or chemistry for doing problems, you may be using log 10. I don't know whether you still use that, but at least in chemistry, maybe for calculating pH values and all that, you use log 10, I think. So that is because we have a decimal system. So with respect to the decimal system, log to the base 10 makes sense, because we normally think in powers of 10. Even our digits, the way we write is that is based on powers of 10. But in calculus, so in maths in general, log to the base e is more natural, because e to the power x is a very fundamental function. As we already saw, e arises naturally as a certain limit, and when you differentiate e power x, we get e power x again. We did that, yeah. When you differentiate e power x, we get e power x again. So that makes it a special kind of function. So log to the base e is the inverse of that, which is natural. So you can write ln if you prefer, or you can just write log. It means the same thing in mathematics. So if you want to write a different base, you have to specify. If you want to write log base 10, you have to write that. So that would be different. Okay. Now this is the inverse of exponentiation. Similarly, what are the other functions? Trigonometric functions. So they also have inverses. So let me briefly define what an inverse is, although you have studied this before. So the inverse of a function okay, if f is a function, or you can write f of x is a function if you prefer, then the inverse of f is, in fact, it's, if it's actually inverse, it is the function g such that f of x is equal to y if and only if g of y is equal to x. That is, f of g of x equal to x. Actually, I should write g of f to be consistent with the notation I already used. I'll write it as g of f of x equal to x, and f of g of y is equal to y for all x and y in the domain and codomain, okay, respectively. That's understood. Then we write f inverse. So for g. So as an example, if f of x equal to log x, sorry, f of x equal to e to the power x, then f inverse of y is equal to log y. I'll use, you can write x also, there's no problem. I just want to differentiate between the domain and codomain. So I'll write y here. Okay. Path, you're asking derivative of sine of x square, right? Not sine x the whole square. Sine of x square derivative is 2x cos of x square. Okay. Okay, now what else is there? There is then inverse of sin x is, we don't have any other name for it, like log is the name of the inverse of exponentiation. We don't have any other name for it. Here we just say sin inverse of x. Okay. So for example, what is sin inverse of 1? So the question is, what is theta such that sin theta is equal to 1? Theta is 90 degrees, or in radians it is pi by 2. So actually in calculus it's important to use radians. Okay, so sin inverse of 1 is pi by 2 in radians. We will use radians always. If you prefer, you can write 90 degrees. But if you're ever doing any computations, then please use radians. Sin inverse of 0 is 0. Okay. There is another notation for sin inverse x. In fact, it's arguably a better notation. Although we'll write sin inverse because that's probably what you'll see in the paper. So arc sine of x. So this is another notation, which is better only because although this is a general notation for inverse, in the case of sine and cos and trigonometric functions, we are writing sine of x the whole square as sine square x, right? But then sine inverse of x is not at all equal to 1 by sine x. So that notation, it doesn't work like that. Sine square x means sine of x whole square. But sine inverse x does not mean sine x to the power of minus 1, which would be 1 by sine x, which is cosecant x. So we don't use this notation to mean that. We use this to mean inverse only. So usually to avoid confusion, arc sine of x is used as a different notation for sine inverse. Now arc is not a separate thing, it's just arc sine of x. Arc sine of x is the name for the inverse function. Okay. So because this this angle is there, the angle can be thought of in terms of an arc of a circle. So if you draw a circle, then for example, this arc corresponds to pi by 2. Okay, and if you take a circle of radius 1, then the length of the arc is actually this angle. If you take circle of radius 1, the length of the arc is exactly the angle, no matter, not only for pi by 2, for anything. If you take any theta, if the radius is 1, this arc length is equal to the angle theta. Theta is actually a dimensionless quantity if you think about it in units, and this is this length of course has the units of length. But if you take 1 as the radius, what actually happens is you're essentially dividing this length by 1. That is equal to theta. So the unit is there. Okay. So this length will be equal to arc. So that's called arc sine x. So similarly, arc cosine x and arc tan x and all that. But we'll use sine inverse for now. Only this is not reciprocal. Understand it. So now the question is, these are also elementary functions. So how do we differentiate them? How do we find the derivatives of these? So for that, you use the next property of the derivative, which is actually it comes from a property of the limit, but we are not proving those. So the property of the derivative is, don't remember the number of this property. So if you have y is a function of x, then x is also a function of y, right? That's what this says. If y is f of x, then x is g of y or f inverse of y. So you can very well ask, what is the rate of change of x with respect to y? So normally till now we have been asking, for example, when we initially defined the slope, we thought about as you move forward, how much do you have to move upwards along the curve? That ratio is the slope. So rise upon run, right? Delta y upon delta x. In the limiting case, that is the exact slope of any curve. That is dy by dx. But you can all trace it in the other way also. As you move up, how much do you move forward? So run upon rise. That can also, in fact, one of you asked me, I think, that why don't we take that? Why is not that not considered? That can also be considered. Only the convention is that slope is defined that way. Probably because when you normally, because of gravitation, when you normally think about slope or steepness, you're concerned with how much you have to go up, work against gravity, right? That's probably the only reason for considering that as a convention, but it's only a convention. You can also mathematically, there's no problem with considering this. This is not called the slope, but it's as good as that, right? It's if you know this, then it's reciprocal slope. And so what is dx by dy? How do we find dx by dy? Actually, what is it? By definition, it should be limit as delta y approaches 0. I'll write x only, okay? X of y plus delta y minus x, where this x actually stands for the function, minus x of y divided by delta y. This is a definition. What we find is that we do not have to compute this from first principles. This actually turns out to be the reciprocal of the derivative. So it is 1 upon dy by dx. Now this may look too trivial because obviously dx by dy is the reciprocal of dy by dx, but it doesn't work like that, because remember, I mean, that doesn't count as a proof, because remember that this dy by dx is not a division. It is a notation for this kind of limit, right? So both of these, the LHS, this is a limit and this is also a limit. So it's not by definition the reciprocal of this. Both are limits. Only the property of limits itself is such a way that if you take reciprocal of a limit, you get limit of the reciprocal, provided some conditions are satisfied. Some basic limit should exist and all that is there. So reciprocal of a limit is also limit of the reciprocal for those functions. That's why this works. Okay. Anyway, once you understand this property, how do we use it for finding derivatives of inverses, right? So what we do is, for example, let's start with e to the power x. No, I'll start with log of x. So I'll write y is equal to, I don't want to write x as log y. I will write y is equal to log x. And the question is, what is the derivative of log x? What is dy by dx? So what we do know is that we know only one definition of log. That is, it is the inverse of the exponential function. So y equal to log x can only mean one thing, which is that x equal to e to the power y. E to the power y, not e power x, e power y. This is the only meaning of y equal to log x that we know. Otherwise, this is just a word, right? It doesn't mean anything else to us. So this is the actual meaning. And we do know the derivative of e to the power x or exponential function, e to the power y, whatever it is, we know the derivative. So what we can find is dx upon dy, which is this. And what is the derivative of e power y? It is e power y itself. Okay. Therefore, if dx by dy is equal to e power y, what is dy by dx? This property tells us that dx by dy is reciprocal of dy by dx. So dy by dx is reciprocal of dx by dy, right? You can also write this in the other way. Dy by dx is 1 upon dx by dy. The symbols don't matter. You can interchange x and y here. So if you want dy by dx, and we know dx by dy, and clearly this is reciprocal of this, which is 1 upon e power y. Now, is this fine as an answer? Not really, because y is log x, right? We are defining y in terms of x, so derivative of y should also be in terms of x. But that's very easy, because I said just now y is log x. So this is 1 upon e to the power of log x. But what is e power log x? X, because e to the power and log are inverse functions. Or you can take it from here also. We already noticed that x is e power y by definition. So if you substitute that here, directly you get this is 1 by x, right? 1 by e power y, but e power y is x, so this is 1 by x. So that is what we have just found is the derivative of the natural log of x is 1 by x. So we have now one more standard derivative in the list. Okay, derivative of log x is 1 by x. Is this understood? This first example. It's particularly simple because the derivative of e power y is e power y itself. It didn't change to something else. So we could just use this directly. In some other problems, we'll have to do some little more computation in other examples. Okay. So the question is, why didn't we use first principles here? Yes, e power log x is x because log is the inverse of e. E meaning not e as a number, the exponential function. Log x is the inverse of e to the power function, right? So they cancel each other out. E power log x is x, and log of e power x is also x. Okay, then yeah, why didn't we use first principle method? So if we had tried to use first principle method, what we would have is limit to find the derivative. We would write limit delta x approaches 0, or let me use h, limit h approaching 0, log of, this is log of x plus h minus log x divided by h. Now what can we do with this? Log of a plus b, do you know any expansion? Don't say log a plus log b, that is log of ab, right? Log of ab is log a plus log b, but log of a plus b is not anything like that. Yeah, and it's definitely not log a times log b. Okay, log of a plus b cannot be expanded easily in that way. So the only other thing I can think of doing here is using this in the inverse way. So log of x plus h is here and minus log x is there. So at best I can combine this numerator and write it as log of x plus h by x, which can be written as log of 1 plus h by x. Which doesn't really help, right? You can divide the numerator by xh. Divide the numerator by xh. You mean what? Yeah, you can divide it by h, or if you can multiply and divide it by x also. But that still won't give us a limit. I don't think we have actually done any limits using log. So that's another problem. Even if we get something like this, we don't have any actual limits which we have done in terms of log. But so first principle method is anyway not easy anyway, whereas this is very easy. Okay, so this is uh, slightly indirect because given this y as a function of x, we first have to write x as a function of y. Then find its derivative, take the reciprocal, write that in terms of x again. So it's indirect but not difficult. Okay. So similarly, how do you compute derivative of inverse trigonometric functions? So what are the derivatives of sine inverse x? So I'll write this as two questions. And derivative of cos inverse of x. And similarly the others, tan and secant and so on. Okay, let's just do these two. Actually, I'll do the first one and leave this as homework. So it's very similar. So for y sine inverse x, first we start by writing y equal to sine inverse x. And then we write x in terms of y. So x is then equal to sine y by definition of inverse. In all of these cases, whenever you're using inverse function, you have to use definition of inverse, which means if y is f inverse x, x is equal to f of y. Okay, then we know dx by dy is cos of y. So dy by dx is 1 by cos of y. The only last step is you cannot leave the answer in terms of y. You have to write it in terms of x. So of course you can write cos of sine inverse x, but there is an even better way of writing it. That's not satisfactory because you can actually write it in another way. What is the relation between cos and sine? Remember, cos square theta plus sine square theta is 1. So cos square theta is 1 minus sine square theta, or cos theta is square root of 1 minus sine square theta. Okay. So here cos square y can be written as 1 minus of sine square y. What is the advantage? Why am I writing in terms of sine? Because x is sine y. So this is 1 upon square root of 1 minus x square. Okay, so what did we get? ddx of, I'm sorry, ddx of sine inverse x equal to 1 upon square root of 1 minus x square. Okay. Similarly, compute this as homework. And if you want, you can try the others also, tan inverse and those also. In fact, tan inverse also should not be difficult. Cot inverse is similar to that, and then secant inverse and cosecant inverse. But yeah, the final, nothing else is difficult there. Only the final simplification, you have to remember these identities and use them properly. That's the only thing. Okay. So this one is almost the same thing. There's hardly any difference. Tan inverse is also easy enough. Please try those. We'll discuss